All right, well, it is officially, as a pulsar timer, keeping accurate time here, so it's officially 3 UTC. So we will get started with Amaldi15. Welcome, everyone. I'm Scott Ransom. I'm the LOC chair. So we have just a few quick announcements first, and then we'll get going with our first session. So first off, I'd like to welcome Joe Vandenbrand, the current GWIC chair. Joe.
Yeah, good morning or afternoon or evening, everybody. I'm happy to welcome you to the 15th Amaldi Conference. So it's an honor of Eduardo Amaldi, and it's organized under the responsibility of GWIC. GWIC is the Gravitational Wave International Committee, and its members are actually representatives of collaborations that are working in gravitational waves. So ground-based, these are representatives from LIGO, Virgo, Kagra, and LIGO India, but also the third generation instruments like Cosmic Explorer and Einstein Telescope. For space-based, it's LISA and DCIGO. And then, of course, the PTAs, the Nanograph, the European PTA, Oxgraph, and the PPTA, International PTA, and probably soon the Indian PTA. And there's also representation from theory. We have some affiliated members. So, for example, the working group or the affiliated commission of the International Society for General Relativity and Gravitation, and also the International Astronomy Union. And GWIC is a working group of IUPAC, that's the International Union of Pure and Applied Physics. So the idea behind GWIC is to facilitate international collaboration and cooperation in the construction, operation, and use of all the major gravitational wave detection facilities worldwide. So that is the ambition. So the Scientific Organizing Committee has put an interesting program together. Most importantly, maybe the PTA recent results will be discussed extensively. And also the ground-based detectors, they just started their 4th science run. Unfortunately, without Virgo and Kagra for the moment, but first detections are already coming in. And then LISA is doing well on the preparations for launch. So I think our field is thriving, and I wish you a very interesting and exciting Amaldi meeting. There's also, so it's every 2 years, and we award also the 2022 GWIC Brancini Thesis Prize. So that will happen on Thursday in session 14, and also then the prize winner will give a short presentation on her work. So let me end by thanking everybody that made this possible and worked hard to realize this. So with that, I would like to give it back to Scott.
Right. Yeah, thanks a lot, Joe. I don't think right now we have any questions or anything. So we'll get ready for our first session. So our first chair is Vaishali. So Vaishali, you can unmute yourself and show yourself if you want, and introduce yourself, and we'll get these talks rolling.
Hi everyone, my name is Vaishali, and good day and welcome to the focus session on ground-based interferometers. To welcome everyone to the first invited talk of this session, it's my pleasure to invite Edwige Tournefier from LAPP, who will present a broad overview on ground-based interferometers. So please go ahead, Edwige.
Hello, everybody. Thanks. So first, I would like to thank the organizers for inviting me to give this overview of the current terrestrial gravitational wave interferometers. So here is what I will take you through. So first present the LIGO, Virgo, and Kagra network, which shows the terrestrial gravitational wave detectors, and then talk about the upgrades and the commissioning that have been going on for the presently starting OFO data taking, give the status, and then finish with prospects and the conclusions. So the terrestrial gravitational wave detectors or kilometer scale interferometer, which are located all around the Earth. There are the 2 LIGO detectors in the US, Virgo in Italy, and Kagra, which is an underground detector in Japan. And there is also the smaller GEO detector that I will briefly talk about as well. So here is the timeline of this network. So the color boxes show you the scientific data taking, which are called the so-called O runs. So we are now starting the O4 run after a long break of almost 3 years of detector upgrades and commissioning, and this is mainly what I will talk about starting from the end of the O3 run. So these are the detector sensitivities that we had at the end of the O3 run. So this is the strain, which means the relative displacement that the detector are sensitive to, which has best sensitivities around a few 100 Hertz, in the region of 100 Hertz, of a few 10 to the minus 24. The blue and red curves show the LIGO sensitivities. In purple, you have the Virgo sensitivity. In black, Kagra. In black, GEO, and in yellow, Kagra. At the end of the O3 run, we had accumulated about 90 events, most of them binary black holes. One very famous BNS, GW170817, and one neutron star black hole event. So before telling you what has been happening before the O3 and the O4 run, let me just remind you the basic of those interferometers. They have some differences, but the main principle is the same. They work on they are all based on Michelson interferometers, tuned on the dark fringe, so that when a gravitational wave passes, it induces a difference in arm length, which produces some power on the dark fringe, which is detected at this output port by a photodiode. And they are all a kilometer long scale arms, sorry. So they are all much more complex than the basic Michelson interferometers. They have in the arms Fabry-Perot cavities, which allows to increase the effective length of the interferometer to be more sensitive. They all use the power recycling technique, which means that as we are tuned on the dark fringe, most of the power is sent back towards the laser, and as the addition of this power recycling mirror allows to recycle the power so that the effective stored power inside the interferometer is increased by the power recycling gain. And progressively, they all use also the signal recycling technique, which is with the addition of this signal recycling mirror, which is used to enhance the signal by recycling, by sending it back towards the Fabry-Perot cavities. So the test masses are typically blocks of 40 kilogram fused silica mirrors that you can show here, which are suspended to 10 meters long suspension to isolate them from the seismic noise. And everything is located under vacuum. They're also progressively using quantum squeezing technique in order to enhance, to increase the sensitivity, and I will tell you more about this technique in a minute. So the fundamental noises which are limiting those interferometers are schematically represented in this kind of simulation, sensitivity simulation here. So typically we have quantum noise, which has two components. At high frequency, we find the shot noise, which is due to the photon fluctuations. And at low frequency, the quantum noise is dominated by the radiation pressure noise, which occurs which is due to the power fluctuation of the laser on the mirrors. Then we have the thermal noise, which is made of two components, the thermal noise from the mirrors and the thermal noise from the suspension to which the mirrors are attached. We will focus in this talk on the mirror thermal noise, which is the limiting one nowadays. So this thermal noise is mainly due to the thermal to the surface fluctuation, which is induced by the non-zero temperature of the mirror, and which is seen as the displacement of the surface of the mirrors. And it's mainly limiting in the 100 Hertz region. So the upgrade of the detectors are mainly focusing on reducing those two fundamental noises, the quantum noise and the thermal noise. And for these, several upgrades have been are taking place. To reduce the quantum noise, we typically increase the laser power, which allows to reduce the shot noise at high frequency. And we use also the so-called quantum squeezing technique. Then we also work on the mirror coatings in order to reduce the thermal noise, and we can also increase the beam size to reduce the impact of the thermal noise, thus averaging it on a larger size of the mirror. And there are also many upgrades which are aimed at reducing the technical noises which are due to, for example, laser noises, but also electronic noises, control noise, scattered light, and so on. I won't go through all of them, but you have to keep in mind that this is also a large fraction of work during the upgrades. So just a few words about the quantum squeezing technique, which is aimed at reducing the quantum noise. So the quantum noise is actually arising through vacuum fluctuation, which enters through the output port. So here this round shows you the fluctuation of those quantum fluctuation which enters the interferometer output port. So it's made of fluctuation in phase and in amplitude. So the phase fluctuation will give rise to the shot noise, and the amplitude fluctuation will give rise to the radiation pressure noise. So if we manage, thanks to the Heisenberg inequality, we are able to reduce when we need to keep the size of this this noise the same, but we can squeeze the noise so that it's mostly in one quadrature. So we can inject squeezed quantum noise, which fluctuation will be reduced in one quadrature. So for example, the phase quadrature, which will allow to reduce the shot noise. And this is what was done during O3 with a technique that I won't explain here. So this is this plot here is illustrating the result of this technique. You see in black the sensitivity of LIGO, I think it's L1 interferometer, without using the squeezing technique. And in green, you have the sensitivity with this what we call the frequency independent squeezing, because it's squeezing only it's squeezing in the same way at all frequencies. And you see the gain of about 3 dB in high frequency. This shows you the Virgo optical configuration during the O3 run. The LIGO configuration was very similar, except that it had also already the signal recycling mirror, actually since a long time. The input power of those interferometers is typically around 20 to 40 watts. And there is one difference also between Virgo and LIGO, to which I will come back later in this talk, which is in the recycling cavities. LIGO is using actually more complex cavities, which are stable recycling cavities, while Virgo is using marginally stable cavities, and I will explain later what it is exactly. All right, so then, so in the past 2 and a bit years, almost 3 years, the detectors upgrade have been installed, and then we had around 2 years of commissioning. So the main upgrade between the O3 and O4 run were dedicated to the quantum noise reduction. So with 3 main actions. First, increase the laser power, and then also change technique for the squeezing with a more complicated technique, which allows also to act on the low frequency part of the spectrum, to which I will come back also. So this is called the frequency dependent squeezing, for which we need to actually install additional cavity of about 300 meters, and also improve all the optical setup, which is so that it has very, very low loss. In Virgo, we also installed the signal recycling mirror in order to use this signal recycling technique, which allows to increase the bandwidth of the detector, as is represented here. There was all the upgrades through which I will not go through, aimed at improving also the technical noises and reducing in general the optical losses of the interferometer in order to have a good performance of the squeezing system. So this is an example of the aim between O3 and O4. So the blue curve shows you the O3 sensitivity, and the red what was the O4 aim. So at high frequency, the aim was to reduce the shot noise by doubling the laser power and injecting more squeezing. At low frequency, the work was also reducing radiation pressure through also the squeezing and reducing the technical noises, and in the intermediate frequency reduces the technical noises in order to go from typically 130 megaparsec to 190 megaparsec. The first main upgrade was, so I will go through all this set of upgrades and tell you a little bit what was the achieved, what it was exactly, and what was the achieved performances. So the first one was this frequency dependent squeezing. So as I said before, with the frequency independent squeezing, we managed to reduce the quantum noise at high frequency. If you wish to reduce also the radiation pressure noise, then you need to squeeze this so-called quantum noise ellipse in the other direction. So you need to have a frequency dependent squeezing, rotating the ellipse by 90 degrees. And this can be done by before injecting the squeezed vacuum inside the interferometer, you need to inject it through a filter cavity, which is detuned from resonance. And by detuning it from resonance with a proper frequency, which corresponds about to a frequency where the two quantum noise meet here, you can actually, this is going to induce a phase difference, a phase rotation, and this will rotate the ellipse and induce frequency dependent squeezing. So the main upgrade consisted in adding this 300 meter long high finesse filter cavity to achieve this goal. And this shows you in the pictures what was done during this long shutdown. Also, I should also add that this squeezing technique is very, very sensitive to losses. So we need to be very careful with all the optics elements that we install on the path of the squeezing so that they have very low loss, which means well below % losses. So this is, for example, very low loss Faraday isolator. Also, mode matching actuators in order to decrease the losses due to mismatching. Also improving the output mode cleaner cavities, which are used to clean the gravitational wave signal so that they have very, very low loss of the order of the %. And here you see also a picture of this filter cavity with the filter cavity mirror and the suspension. And the aim was to achieve a quantum noise reduction of about 4.5 dB. And this is the result of all this work. Virgo and LIGO both managed to get this technique working. LIGO is a bit more advanced, as it has already injected the squeezing inside the interferometer, and you see here the result. In black is the sensitivity curve without any squeezing, and in green is with the frequency independent squeezing, and in purple with frequency dependent squeezing. And you see that with the frequency dependent squeezing, you manage to improve the sensitivity at high frequency and also at low frequency, and at least not deteriorate it with the radiation pressure noise at low frequency. A paper is in preparation with this result. In Virgo, we have demonstrated also about 6 dB of squeezing in standalone, which means before injection inside the interferometer, and we still need to increasing. So on this curve, what you can, the performance is shown by the envelope of all these curves, which shows you the level of squeezing which can be ejected, and these results have been published also. So that's it for the frequency dependent squeezing, which is a big success. Now I'm going to talk about the other upgrade, which is about the laser power increase and its induced effect. So the laser power, has been increased in all interferometer, and this means that more power is absorbed in the optics. So our optics have very low absorption of the order of the ppm, but as we increase the power, the effect of this small power increase has some thermal effect. So there are two thermal effects. One, which is due to the absorption, is the substrate, which induces a thermal gradient and a lens. And the other is due to the absorption into the surface of the input test masses, which induces a change of radius of curvature. So the most effect is in the input test masses, as these are the test masses which are which see more power because they are inside the Fabry-Perot, and the beam goes through those test masses. So this is very annoying, as this distorts the wavefront, and this increases the losses and limits the power that we can store inside the Fabry-Perot cavities, as you see here on this curve, which shows the arm power, so the Fabry-Perot arm power, stored power as a function of the input power. And you see in this blue curve that even with some thermal compensation of this effect, we cannot, we are limited with the power that we can store in those cavities. There is an additional effect, which is non-uniform absorption, which is due to point absorbers that we have found out during the O3 run, which shows due to some small particles which are embedded in the coating of the mirrors, and which induce some local deformation, which is even more annoying because it's much more complicated to correct. So as I said, we correct for those thermal effects. So we have what we call the thermal compensation system, which are CO2 lasers, which are which will correct for the lens effect inside the input mirror. So inside the input mirror, which we have the lens effect, which is due to the absorption. In front of them, we have compensating plane on which we shine those CO2 laser, which with a kind of donut shape, in order to have the opposite effect of the opposite lens effect. And in order to compensate for the deformation of the surface, we also have installed ring heaters around these input test masses to correct for the radius of curvature. So it works reasonably well, with, of course, some limitations in the sense that you cannot perfectly correct, and that's why we in any way are still limited by these effects. The second thermal effect, as I said, is due to the non-uniform thermal effect due to these point absorbers, which have been so a long study has been done in order to understand those and characterize those point absorbers, and it turns out that some of them were due to some kind of aluminum particle which are embedded in the coating, which is deposited on the surface of those mirrors to obtain the reflectivity. A long improvement of the coating deposition process took place in the laboratory, the LMA laboratory, which is coating all the gravitational wave interferometer mirrors. And in LIGO, it has been decided to characterize and replace some of the Fabry-Perot mirror which had most of point defects. And it was quite a success, because with the new coating process, this problem has been reduced. And you can see here, so this shows you the input laser power, so the power store in the arm as a function of the input power. And you see that in O3, it was limited by these point absorbers. And after the replacement of, I believe, the mirror with most point absorbers, you see that it was possible to increase, to have a much more linear correlation between the amp power and the input power, showing that the impact of those point absorber was well reduced. And actually, for O4, LIGO managed to increase input laser power up to 60 to 70 watt, which means the 400 kilowatts stored inside the Fabry-Pérot cavities. In Virgo, we have not replaced the mirrors, but we have decided to go for another option, which is to compensate for those point defects. So this is another actuator which has been installed, which is also sending heating the test mass with a pattern which is the opposite of the pattern induced by the point absorbers, and it has just been installed and it still needs to be commissioned, so it's not been proven yet to work, but it should in principle allow to compensate and correct for the loss, most of the losses induced by those point defects. Now I'm going to change topic and talk about something else which is related to the increase of laser power and which is the recycling cavities. So as I said, LIGO is using stable recycling cavities and Virgo marginally stable cavities. So in LIGO, the cavities are actually made of much longer than in Virgo and made of much more optics. We have telescopes inside the cavities, which allows to accumulate some GWIC phase and separate the fundamental mode from the higher order modes of the laser. While in Virgo, those cavities are much shorter, which means that the higher order mode will resonate in the same airy peak as the fundamental mode, and they are not much separated, so the higher order modes will resonate. And as you increase the power due to those thermal effects that I was just talking about before, you have more higher order modes, and this higher order mode will be therefore enhanced and create distortions inside on the signals, on the interferometer signals. There are several effects which have been observed due to the marginally stable cavities. Sorry. First, is the resonance of those higher order modes. So this creates optical offsets on the error signal, which will depend on the thermal effects and also on the alignment, because it depends, for example, if your beam is far away or close to a point absorber. It will distort the error signal, and it will also lower the gain of the fields, because you lose signal in your fundamental mode. All this put together will increase the technical noises through the controls. Another effect is that the higher order mode will resonate inside the signal recycling cavity, so they are enhanced, which will degrade the contrast effect of your interferometer mode of your interferometer, and will also increase the technical noises. It will also create more instabilities, because as you get closer to the stability region, to the well-tuned thermal state, you enhance the instabilities. And we're also wondering whether we have extra losses in the signal cavity, the signal recycling cavity, which might impact the squeezing. So all this has led to a much slower commissioning, because it was all unforeseen effects which we had to understand, and also we reduced the input power in order to have less impact of those thermal effects of those thermal and recycling marginally stable recycling cavities effects. Nevertheless, as you can see here, The use of the signal recycling has allowed to enhance the bandwidth of the detector. So the purple curve shows the O3 sensitivity, and the blue one is the one which was achieved with 404 with the signal recycling technique. So that's all for the I will say for the upgrades. So as I said, due to this slowed down commissioning, Virgo decided to join OFO a bit later in 2023 in order to further improve the sensitivity. So the path towards OFO is now to lower the control noises, which are limiting at low frequency, lower the shot noise and the laser noise, which is limited at high frequency. And in the intermediate region, we have some unknown noise, which might be of thermal origin, but it's not clear yet. And we still have the step of also injecting the squeezing. So this is for Virgo. On the LIGO side, this is an example of the instrumental noise. This is so all the technical noises here are shown with those colored curve. The fundamental noises are also shown here as quantum noise, thermal noise, and you see that LIGO is mainly limited by those fundamental noises, and you have all the control noises, which are still a challenge at low frequency, and they're still working on this. And there is some unknown noise also in the intermediate region, which it's not clear what it is as well, and which they are trying to understand. So that's it for LIGO and Virgo. Now I will say a few words on the Cagra interferometer. It's a bit different, that's why I didn't talk about it at the same time as LIGO and Virgo. It's a kind of 2.5 generation interferometer in the sense that it's already underground and it's using cryogeny. It's also recycled with 3 kilometer long Fabry-Perot arms, and the use of the cryogeny. The aim of cryogeny is to lower the thermal noise of the mirrors. And in order to be able to use this low temperature, the mirrors are made of sapphire instead of silica, as it is in LIGO and Virgo. So this is important because this is a new testing new technologies. So during O3, Cagra was operating with low input power and with only power recycling Fabry-Perot interferometer, and they discovered several issues. First one was that cryogeny was not working as expected because it was resulting in frost on the mirror. So they finally operated at room temperature while understanding how to solve this issue. And they discovered also that they had birefringence, as shown here on this on the input test masses. So due to these birefringes, this induces large losses and also large coupling of laser noises, which led to a poor to worse sensitivity compared to what they expected. And also the suspension control were not as stable as expected. So during the commissioning, Cagra worked on all those topics. The suspension control has been improved. So the stability of the interferometer is much better. The frosting issues have been solved through improved vacuum and much also improved procedure to cool down the mirrors. And there were also improvement aimed at improving the instrument noise, all the technical noises of the instrument which are illustrated on this figure here. So the status now is that all those improvements have been successful. The color curve here shows you the progress in sensitivity between 03 and 04, and the aim of 1 megaparsec has been reached. Nevertheless, CAGRA has also decided to join. They started by a couple of weeks of data taking at the beginning of 04, and then they stopped to go on with commissioning to further improve the sensitivity later in 2024. The plans are still under discussion, but basically the idea is to increase the laser power to operate with cryogeny now that the problem is solved, and also to improve the controls. There has also been some work on improving the sapphire mirror and reducing the birefringence. As you can see here, the birefringence have been much improved with some new substrates which have been produced. And these will be installed for 05. So this is the main upgrade for 05, and which will lead to much improved performance. And the mirrors will be made also much more symmetric in terms of reflectivity, which will allow to lower the laser frequency noise at high frequency. And they are also thinking about adding the signal recycling mirror. So just one word on GEO before concluding on the upgrade, on the round of the overview of those terrestrial detectors. So GEO is similar, except that it has no Fabry-Perot in the arms and it's shorter. It's using also frequency independent squeezing, and it's focusing on high frequency operation. And it is actually in what we call the AstroWatch mode, which means it's continuous data taking. And it's also testing new technologies, which then are installed on the larger interferometers. So the 04 run started 1.5 months ago, and it's going to last 1.5 years. The obtained ranges are ranging from 1 megaparsec for CAGRA to 120-160 megaparsec for LIGO. Virgo is around 25 megaparsec presently. And this shows you the PNS range over the last 1.5 months for the two LIGO detectors. As I said, CAGRA is in commissioning again to improve the sensitivity, and Virgo also decided to join later, as the commissioning was slowed down by the use of marginally stable cavities, and it had to solve two problems, also with two test masses that I didn't talk about, but which took actually quite some time. So these are the sensitivities that we have now for all those detectors, which are much improved compared to 03. And so what next? So this, so as I said, the run is gonna last for 18 months. And during this run, we are preparing the next set of upgrade, which will be installed for the 05 run. And the main aim of this upgrade is the reduction of thermal noise. For this reduction of thermal noise, the big upgrade is really to lower the thermal noise of the mirror, which is mainly limited by the coating thermal noise. Also, as I said, there are some point defects on those mirrors, which are very annoying as they induce thermal effect, and these will be also reduced, and this should allow to further increase the laser power. There are also upgrades, of course, which I will not go through. So just one word on the coating upgrade. So as I said, the coating is the main limitation in the thermal noise that we have in the 100 Hz region. There is a quite challenging R&D ongoing to reduce this thermal noise. Not only you have to reduce the so-called loss angle of the coating to reduce the thermal noise, but also you have to make sure that this coating has low absorption, low scattering, and no point defect. So this is pretty challenging. And so the coating is actually made of few layers of alternating high and low index refraction index layers. Made of the actual one is titania, tantania, silica layers, and the aim is to replace those materials with advanced material which have low thermal noise by a factor 2. So we have found a new candidate to replace the highest source of thermal noise in these coatings. The challenge is that there is a quite complicated deposition process, and it needs to be annealed at high temperature, and there are many challenges in this deposition process, and the coating can lose its high good qualities through these processes. For example, we see now the formation of kind of bubbles in the coating, which are of course which we don't want because it deteriorates the quality. So there is a long investigation in the all these procedures, and the properties are not yet satisfactory. The absorption is too high, there is too much scattering due to those blisters, and we are actually still investigating the possibility of using other candidates. So this is a long and challenging R&D process which is still ongoing. One other upgrade which Virgo is thinking about doing for 5 is to install stable recycling cavities, because as I said, and marginally stable cavities limit us in the power that we can inject in the interferometer. So these studies are just starting, and there are several options which are envisaged. So that's it. Just one word on the longer term plans. We are actually also preparing further upgrades after 05, but Bram, the next talk will be on this topic, so I'm not talking about it. And to summarize, after the 04 run, we have had 3 long years of upgrades and commissioning of the LIGO, Virgo, and Cagra detectors. Several challenges have been discovered. Frequency-dependent squeezing for quantum noise reduction has been a success. It is performing well. The increase of laser power is, on the other hand, a challenge, and we have progressed, but there are still challenges ahead of us to really manage to manage this increase of power. And all this requires very careful simulation studies to properly understand the behavior of our instruments and to improve it. So the 04 run started with increased sensitivity, with the BNS range about 120 to 160 megaparsec for the LIGO detectors, and Virgo and Cagra will join later. There are upgrades in view of 05 focusing on the reduction of mirror thermal noise, which is quite a challenging R&D, but progress are ongoing there. And Virgo is also planning the installation of stable recycling cavities. And the last set of upgrades is being prepared for the post-05 area. And to finish, I would like to thank Lisa Barzotti, Mark Eisenmark, and Raphael Emil Flaminio for their help in preparing this talk. Thank you.
Thank you so much for that extremely comprehensive talk, Edwige. Are there any questions? I don't see any hands up. We have about 5 minutes for questions if people have questions. Maybe I can, since I have the privilege of chairing, maybe I can ask you a very quick question. Since you very rightly mentioned that loss is very important for squeezing, do you have an estimate off the top of your head how much the loss was changed between, or how much it was decreased between 03 and now? The loss in the squeezing path.
Yes, I think that in 03 it was about 30 to 40%, and now we have reached about 15%. So it was decreased by more than a factor 2.
Oh, that's,
yeah, if some
such an
experts in
effort
the
to get
room,
those.
yes, it's really the total. There are the losses which arise in the squeezing system, and then there are the losses which arise inside the interferometer. And so at the end, it adds up to, even if each component is below the percent, it adds up with quite a big amount.
Thank you so much for that. I don't see any hands raised or questions. So let me thank you again on behalf of all of us for a really lovely talk.
Thanks a lot.
And I'd like to invite the next speaker, Bram Slagmolen. Would you like to share your screen, Bram?
Shall I? Yes.
And while Bram shares his screen, I'd like to welcome Bram for the session. And I guess Bram will be presenting the next decade of ground-based interferometers. And the floor is all yours, Bram.
Can you see my screen and can you hear me clearly?
Yep, I can. And I see your screen as well.
Excellent. Thank you very much for sharing. Thanks, everyone. Thanks, the organizers, for inviting me to speak. And I will speak on behalf of the LVK on the ground-based interferometers the next decade. I'm Bram Slagmolen. I'm an instrumentalist at the Centre for Gravitational Astrophysics at the Australian National University. In my speakers. Oh, there you go. Yes. So Australia, the ANU is in Canberra, and I myself live and work in Canberra as well. And Canberra is situated in Australia, and the traditional owners are the Namanjir people and the Ngunnawal people. And in Australia, we'd like to acknowledge the traditional owners on the traditional lands we meet, and we pay our respect to the elders past and present and emerging. So the overview of my talk would be about, on the left side, I highlight the 04, but we've got an excellent talk on the previous speaker, so it will be a very fast one. Then we're going on to expanding the LIGO network, followed on by some next ideas we have, and then we're going into the next decade of the next generation observatories with a few technical challenges to come, and then a summary. And here's a list of various people who helped me get this all together. So 04, this slide is a super dense summary of the excellent talk we heard just before. There's actually 2 items I would like to highlight. One of them is that I would like to thank, and we should acknowledge, all the hardworking people on the sites to making those machines to operate at their design sensitivity or at their operating point at the moment, because they put a lot of hours and people power in to get that going, to get, of course, these 04 running. So that's actually a very great achievement. Then at the same time, we have 16 more months to go to see what happens over the time. So that's also an exciting prospect. Now, LIGO and Virgo runs and Kagra, and LIGO has extended their operation to have a LIGO India detector. India received got some initial government funding and a grant approved to actually then starting the LIGO India project. And what happens is that the third interferometer from advanced LIGO will be moved to India, and we will get basically an advanced LIGO detector in India, which will be in the tail end of this decade. And that, of course, then will extend the LIGO detectors to 3 machines, including then the Virgo and the Kagra detectors. And that, of course, it helps increase the localization of the events. In addition, what the previous speaker also highlighted slightly, there are some activities we're already looking into, as of course we're having 04 and then 05 is already on the cards as well. However, what we're going to do post 05, which will be in the around the 20 or 30 regime on what we're going to do. And in LIGO, there is the prospect of an A-sharp detector, while Virgo has a Virgo Next configurations. The idea is that the detector would be about twice as sensitive as the advanced LIGO Plus detector. And on the right, you see the graphs in between, and which have mentioned various of those graphs before as well, that on the left, on the vertical axis, we have the strain sensitivity, and our horizontal axis, we have the frequencies, which starts here from about 3 Hertz up to about 10 kilohertz. And then the blue and the black lines are the sensitivities of the Virgo Plus and advanced LIGO Plus, which should be operating in the not too distant future. And then the post 05 configuration, the idea is to reach that red sensitivity. A sharp, what will that be? That will be very comparable to what we're doing now. It will be a room temperature machine. We're staying at the same laser wavelength, so we don't changing anything there. What actually does happen is that we're going to increase the test mass from currently about 40 kilograms in LIGO and Virgo to about 100 kilograms. That is then, say, a diameter from currently about 40 to now to about 50 centimeter in diameters. The laser power design laser power goes to about 1.5 megawatts. Keep in mind that the design sensitivity of advanced LIGO Plus is about 800 kilowatts. We're actually currently operating at about 380 kilowatts. So we're about 4 times away from the design power, circulating power in the arms as we currently running at. Then at the same time, a sharp will have, because we have this larger test mass of 100 kilograms, we'll have an improved or new set of isolation and suspension systems. And the key ideas there is actually then work out and to reduce the motion and incorporate controls from the start to make sure that when we reach that design sensitivity and that they're all suspended, that the test mass is behaving as we want it to do. Part of that pathway also is then to get lower noise local sensors. So we have a lot of sensors around the place which monitors the mirror position, the Faraday isolated position, the photodiodes, etc. And all those sensors, if we increase the performance, getting a smaller sensitivity than we currently have, then of course you can imagine we can improve the performance, overall performance of the whole device. Then, because we're getting those 100 kilogram test masses, we are gonna need a new mechanical suspension system, as multiple pendulars, etc. And then the idea is that, of course, we're going to use the lessons learned from the previous designs incorporated in new ones to hopefully then get even more improvement mechanically by themselves than the current operating. Well, they're doing great, by the way, but you get even further along. A new thing that A-sharp will utilize is to subtract Newtonian noise by a factor of 2. Newtonian noise is the ground motion, the Newtonian force due to the density change in the ground that then pulls the test mass away from its nominal position. And of course, we can't shield against that. So what we do, we're going to measure the motion of the grounds, and from there we're inferring then the change in density, and from that we then can subtract that potential change of force on a test mass to mitigate that effect. And in the A-sharp and the LIGO scenario, all these technologies are also a pathway towards future next generation detectors in the US. So then for the next decade, what we do is we having done the A-sharp running, the idea is that the new detectors, or the next generation detectors, as we're calling them, have a sensitivity improvement of about 10 times compared that of A+. So we're ignoring the red line for a second. So if we have the black and the blue line, then we're improving across the frequency band, the whole detector sensitivity band goes by a factor of 10 times improvement. And those are then the purple and the green lines in the figure on the right. And those facilities are predominantly the new facilities that we build. They're also in new locations. And of course, we utilize then all the lessons learned again from our current facilities into the future. So the next generation ground-based observatory, as I said, they will have a 10 times improvement over the current design sensitivities. And then with those sensitivities, we can actually see almost all the events in the observable universe. And if you put all the numbers together, then we can almost see all the binary neutron star mergers in the universe. And we almost see most of the 10 and 10 solar mass black hole mergers as well. On the right, you have a cartoon, and although it says Cosmic Explorer, that's of course valid for the Einstein, or the European Einstein telescope design as well. Another way of looking at this is that we're going to probe the early universe. So on the figure in the center, we have here the two events in the local universe, and the Hubble Space Telescope sees to about a redshift of 10. The James Webb Telescope itself sees about to a redshift of about 20, which is just on the borderline of the first astronomical object. And the idea here, and that refers to a figure on the right, we can see in the 3G, the third generation, the next generation detectors, you can see up to a redshift of 7. So you can see on the bottom right, the figure is on the horizontal is the mass frame of the sources, and on the vertical axis the redshift. And we can see if we plot the sensitivities of the strain noise at the top curve and convert it in redshift, and we can almost see to a redshift of 100 with a mass of about solar mass of about 10. So we can see a large amount of the universe, and that of course gives us a lot of astrophysics information and new frontiers to work out what's going on. The next generation observatories have a very similar design idea as the current machines. We will have a dual recycled Michaels interferometer with arm cavities, as the previous speaker has explained. Again, we will have even further increased mass of the test masses. And the biggest change actually is that the arm cavity length will be much larger. Previously, we had about 3 and 4 kilometers. These devices will go in the 10 and the 40 kilometers. There's 2 major projects currently on the way. As the concept stage, so the Cosmic Explorer, which is a US-based concept. And the great news is that recently they have some new funding from the National Science Foundation in the US to actually create that concept and come up with actually a full conceptual design. Then in Europe, we have the Einstein telescope, and that is a large consortium or a telescope which is actually much further along in the design phase and has quite a bit of funding from the European Commission to further design and come up with actually construction or plans to work out what to do. Then we have also some alternative ideas, which is referred as a Voyager and a NEMO device. So the Cosmic Explorer in the US, they construct of the idea, the concept is that there are two sites with each, or one site will have a 40 kilometer long L-shaped detector, while the second site will have a 20-kilometer L-shaped detector. And that, of course, the idea is because we have 10 times longer, we have 10 times improved sensitivity. The main idea is that they will operational in the mid-2030s, and there also the pathway is to use the LIGO and the A# technologies to build up the new performance. And of course, the idea is that in the same fashion as LIGO operates now, that the facility is flexible enough to, of course, upgrade and integrate new R&D breakthroughs. Another highlight is that recently the NSF requested the next generation gravitational wave subcommittee, and there were various white papers in the US submitted to there in support of what to do in the future for gravitational wave detectors. And the Cosmic Explorer white paper is quite a nice read on all the excited astrophysics we can do. So the detector concept of Cosmic Explorer, again, is very similar to the LIGO technology. And here on the right is sort of an optical diagram of how it works. Where again, we have the beams, but in the center, and then the long arm cavities going to north and going to the east. The key thing there is that in advanced LIGO, we're having these 40 kilogram test masses, which of course in AlGaAs about 100 kilogram test masses. And in the future in Cosmic Explorer, there will be 320 kilogram test masses. So the pathway to get those things is still on the way, and hopefully we can then work towards from the 100 kilograms to the larger test masses. The suspensions, of course, will be will be larger as well. In AlGaAs, we'll use the similar housings as for advanced LIGO, and in the Cosmic Explorer, we were using 2 meter long pendulums instead of the 60 centimeter long pendulums. The other idea is, of course, previously we had only 4 kilometer beam tubes, and now we need to get 40 kilometer beam tubes. So there's quite a bit of infrastructure change. With a 40 kilometer detector, we can make a very large broadband machine. However, with 20 kilometer machine, which is on the second site in the US, what we actually can do, we can start tuning the signal recycling length and the reflectivities, and then actually we can start tuning it so that we have an improved sensitivity around the 2 to 3 kilohertz. And that frequency range is actually where the binary neutron star merger ring down happens. So if we can actually then see that ring down signature, we can actually extract other excited astrophysics, if not the equation of states. The Cosmic Explorer, it will have increased, the same L-shape vacuum system, and the idea, of course, that there will be 2 locators in North America, although you can imagine they can go other places. The key thing that we have 2 wide-spaced observatories, the same as currently LIGO operates. Here are some nitty-gritty optical details. And then the key is, of course, that we have still a few silica test masses, same as current advanced LIGO users. The mass, of course, goes from 40 to 320 kilogram. We're operating at room temperature. In Europe, on the other hand, is then the Einstein telescope. And that utilizes, or the current design is an equal lateral triangle with arm lengths, or the lengths of about 10 kilometers in length. And the whole concept also is because Europe is so busy above ground with all the use of the land, various land use, that the idea is to put it on the ground to still maximize the available land. So that will be then placed about 200 to 300 meters, underground. Also, because the equilateral triangle, the idea is to have 3 interferometers in that construction, and with that you can also then do the whole polarization and all with one machine instead of, say, the LIGO or the Cosmic Explorer concept with 2 detectors. The ET collaboration is about 80 research units. There's a little insert in at the bottom right, which have currently about 1,200 members or more. So how ET Einstein telescope operates is actually a very clever design. We actually have 2 different interferometers. So we have a low frequency detector, which actually only then uses on the top right, has a sensitivity, which is just looking at the low frequency and don't care about the high frequency. And with that, we use that operates at cryogenic temperatures to improve the thermal noise behavior, use silicon test masses, we'll get on later on. We use different wavelength and the suspension system, which is much more advanced, much taller. Then at the same time, we have a second interferometer, which is then the high frequency interferometer, which uses high laser power, have much larger test masses, and requires, of course, thermal compensation. However, merge those 2 frequencies, we basically can just use the output and post-process joined the sensitivity curves. Then we're getting here this red curve trace in the center, and hence we construct then a wide band sensitivity of each interferometer. So one interferometer operates 2 detectors, and then you have actually 6 interferometers in total, generating 3 full wideband detectors. So here is then another picture of that, and then in the blue you have then the low frequency, which uses then the lower, that's the right column, the 200 kilograms, the relatively low mass. Different wavelength, use silicon, use at low temperature, about 10 to 20 Kelvin, has about 18 kilowatt circulating power, which is actually very low in current states of interferometers. However, that is then the low frequency. Well, then the red interferometer is the high frequency, which has about 3 megawatts of circulating powers, use fused silica, and of course has that 200 kilogram test masses. And the filters and the squeezing injection is the standard, as Edwige in the previous talk highlighted. A little side note at the bottom, of course, is then for the low frequency, we need to increase that low frequency displacement performance of those test masses. So instead of having the standard 8 meter tall super attenuators, which Virgos operate, the current path forward is using 17 meter tall modified super attenuators. There's quite a bit of excitement going. So these are the next generation detectors. However, there are some alternative concepts that also are of interest. And one of those concepts is the Voyager interferometer. And that can utilize in the same infrastructure as the LIGO, the Virgo, or the Kagra machines. However, they then operate at, say, 123 Kelvin and uses silicon test masses, and predominantly the reason is that will have a thermal expansion of goes to 0, so the heat dissipates straight out of the test mass. So we don't have any thermal deformations as much as we currently have. The challenges is that it requires quite a lot of additional R&D, because we'll also require a different wavelength. So lasers need to be constructed which are stable and operate. Detectors need to be investigated, because if we use longer wavelengths of about 2 micron, as here predicted in the schematics, then 2 micron detectors are far in between. However, ET and another concept uses those similar silicon technologies, so there is a crossbreed. For Voyager, the idea then is to have a silicon test mass predicted here in the center black, and it will have a monolithic system as another silicon at the top. And to have it transmissive or use with a wavelength, we use a longer wavelength of about 2 micron compared to the 1 micron we currently use. We need the test mass with about 200 kilograms, and we have then a circulating power of about 3 megawatts. To cool those down to about 123 Kelvin, the idea is to use radiative cooling. You can't actually have a braid or contact with a test mass because then you are shortening the suspension and isolation performance. So the radiatively cooling is the best approach to do that. An alternative concept is the NEMO concept, which is referred as the Neutron Star Extreme Matter Observatory. And this detector design concept looked at the single science case, and there's that it looks at the merger signature of the binary neutron star at the post merger. So on the right is the characteristic strain on the vertical axis, and on the horizontal axis we have the standard frequency. And in the red is then the binary neutron star signature ring down imposed on the black line, which our detector sensitivity. And the idea is that there you can reconstruct the signature of the post-merger ring down. Of course, and that is then compared with, say, advanced LIGO detector performance. And if this operates in the same time frame as advanced LIGO, then of course you can reconstruct that post-merger signal. However, once the third generation detectors are operational, then there is a limited benefit. The idea is that when it operates during advanced LIGO or A-sharp, then instead of, although this publication is on the blue lines, is the advanced LIGO sensitivity or merger rate or detection rate, event rates, well then NEMO would then see about, one or a few per year compared to the advanced LIGO case. And then there's then the merger happens at the kilohertz regime frequency range. So again, extract and the equation of states is then the excited part that we're after. Of course, there's another exotic astrophysics science to extract from those signals. The design concept is very similar to all the other interferometers. We have an L-shaped, we have a 4-kilometer arm length, and that is then the idea that this concept could sit in a cargo like or Virgo in facility. We have about 4.5 megawatts of circulating power. We're using silicon test masses. We actually have slightly different temperatures of the input test mass compared to the end test mass, and that is more regarding the heat extraction we can do. We also have a long signal recycling cavity, and that is then, of course, and that is then to be able to tune that increased sensitivity at the kilohertz regime, although at the same time reducing or ignoring any sensitivity at the lower frequencies, because all the advanced LIGOs, advanced Virgos are operational, and they actually see the low frequency signal, and then we only look at, or this concept only look at the kilohertz regime. Then there are some general technical challenges that the previous speaker have touched on as well, and they are all valid for the A-sharps and the Virgo Next and the third generation detectors. So one is there, the coding thermal noise, and the following speakers will go into more depth in various depth in this topic. But the general idea is if we have all these fantastic improvement in quantum performance or the squeezing, etc., if we don't improve the coding thermal noise, then we can, using the A-sharp performance curve on the top right, then the purple is the quantum noise limit of the interferometer, but if the coding noise is not improved, then we still be limited by that performance. So at the bottom right, if we then say increasing by about a factor of 2, the coding thermal noise, then we can recover that gain that we then use in all the quantum performance of those machines. And although I had a whole list of various things to talk about, there was too many activities happening in this field, and it's actually it's been on for the last decade, but in the last few years, I have some great strides and results coming out, and hopefully in the not too distant future, various publications will come out with great results. What I want to highlight in the end is that, of course, we can develop new coatings and work out their performance, but in the end, you almost need to build one of those interferometers to work out that the performance is sufficient. However, colleagues at MIT came up with a brilliant scheme to actually measure the thermal noise of a large frequency range, and with that, you can then rescale that to the performance, or map that to the performance in future detectors. So those activities, of course, very important. Then for the not too distant future, the A-sharp scenarios, they're all still using fused silica, as we're using that. Now on the top right, there's a beautiful picture of one of those test masses in LIGO. However, we're going from that 40 centimeter, we're going to about 50 centimeter diameter test masses, so, and about 100 kilograms, so it will be a whole new challenge, of course, to operate those devices, and of course, suspend them from the probe suspension system. If we then increase the circulating powers in those arms, of course, we need to mitigate all the increased thermal effects, what the previous speaker has alluded to, and pathways are to work on those, although in the end, we just have to come up with make it all dance together to make sure that the interferometers are operating, behaving at the operating point. Of course, now one idea is to use the silicon as a potential test mass, although I'm not in the pipeline for the A-sharps and the Virgo Next, because the key driving force is that at 23 Kelvin, the thermal expansion goes to almost zero. And that then, of course, there's no thermal challenge or very little thermal challenges to have. The trick there is, of course, that we need to have then, as I alluded before, longer wavelength laser sources. However, operating silicon test masses or making silicon test masses is still a large R&D effort. With then new lasers, you want to get, there's a pathway to finding new lasers. They are in the 2 micron range. Of course, the 1.5 micron lasers are in the communication field used all over the place. However, if we want to go with 2 micron lasers, they're a little bit trickier to come by. However, there are some efforts underway to have a simple, easy build laser sources, and then we go from there to stabilize them to operate them as we want. To increase the laser power, instead of building one big, large, high power laser, the approach now is to have a low power seed laser, which is behaving and stabilized as we wanted to, and then we cascade multiple amplifiers in series to up the power to the hundreds, the 200s, and the increased levels. Of course, what previous speaker alluded to as well is that we still want to utilize the quantum control of the light into the interferometer to improve the performance, which of course will be utilized in the 1 micron regime. However, for the 2 micron regime, there is need to be sanity checked that works, and the top right and the bottom right figures indicate that that performance is available. The technique and the way to do it is very, very similar to the 1 micron approach. However, you first need to build it to see if it actually works. Then for the low frequency improvements, as alluded to before, is that in Virgo you have the super attenuator, and for the Einstein telescope they want to have a 17 meter super attenuator. So again, there is the new designs to get those test masses performed at lower frequencies. Virgo is then to use bigger or larger or more improved super attenuators LIGO will most likely continue with the active control systems. However, instead of the 100 kilogram quad suspensions, we're going into the couple 100 kilogram quad suspensions, and for Cosmic Explorer, we will need to have 1500 kilogram suspensions. However, in the end, it's not so much the suspension that we actually need to worry about too much, because that will operate. We have the Newtonian noise at the low frequency that we need to improve, and A# will already utilize some of that, but for Cosmic Explorer, especially because it's on the surface, that will require further attention. However, Einstein telescope gets around that to some extent, well, to the most extent actually, because they're going underground. So the surface waves have nominal, no effect into the performance of the test masses on the ground. The other challenge we have is the vacuum system. So because we're building a new infrastructure, we have to build new tubes. And the other day when I put it together, it turns out that we need about 120 kilometers of vacuum tubing. That's quite a long distance. So for Cosmic Explorer, of course, we have two very large machines, so about 40 kilometers and 20 kilometers. And then ET, although it's a 10-kilometer equilateral triangle, we have about 6 of those around the place. So hence you're getting also, again, 120 kilometers, interestingly enough. It is about half of the cost of the whole budget for either of those telescopes or observatories. So coming up with a new scheme to, and that costing is then with current technology. There is efforts on the way is to work out if we can use different materials or different means to create these vacuum systems to reduce, of course, cost and get the same or better performance. So this is the tail end of my presentation. So we had the 4th observing run is on the way, and we are detecting events. And of course, we're all waiting for that event that everyone goes nuts. But I think we still have to wait for that a little bit. At the same time, the future is bright. Detector upgrades are underway. Planning is well advanced in the various Virgo and LIGO laboratories. The next generation observatories are under development. The Einstein telescope in Europe is very far ahead with site selections and constructions of the various labs around Europe. The Cosmic Explorer team in Europe got some funding from the National Science Foundation to actually start constructing some serious plans on how to approach the pathway to Cosmic Explorer. Of course, there are always challenges to overcome, and we always try to mitigate them, but I think the goals are clear what we want to do. We just need to find the means to get there. And I thank you for your attention.
Well, thank you so much for that lovely talk, Bram. Let me see. Are there questions for Bram? Yes, I see one from Tom. Tom, would you like to ask your question?
Yeah, hopefully you can hear me.
Yes, we hear you.
Oh, wonderful. Thanks for that very comprehensive and kind of optimistic overview, Bram. So I guess I have what counts as maybe a small correction about ET and a question about CE. So, I mean, it's true in Europe there is less, let's say, open available land to build interferometers on than in the US, but you could solve that by going maybe 50 meters underground. As far as I know, the main motivation for putting ET 200 or 300 meters underground is the further you go, the less seismic noise, the less Newtonian noise you get. So it's extremely expensive to build this as like a CERN scale project. You get some payoff in terms of like reducing seismic noise. I guess for CE, this may be the first time I've heard about this 40 plus 20 plan. Is there like some reasoning why you could go for just 40, a single big interferometer. You could go for two 40-kilometer big interferometers, analogous to the current LIGO observatories. Is there some sense that like 40 plus 20 is some kind of optimal sweet spot? What kind of, let's say, cost versus benefit versus cost is optimized by 40 plus 20?
Yeah, thanks, Thomas. First comment regarding ET, that is absolutely correct. Going on the ground is mitigating the detector noise challenges, which you otherwise would have on the surface. So yes, that's correct. For Cosmic Explorer, it's more a cost benefit. If you go to 40-kilometer machines, that will definitely be a wishful approach we want. However, with the 20K, you can also then start doing the tuning to a few kilohertz regimes. So there's I think there's a cost benefit to utilize a 40 and a 20-kilometer machine.
Right. So okay, you can point to specific like extra science you can get from this configuration. And that's very interesting, in fact. Thanks.
There's one more, Bram, from Jan Nowak. What is the reason that ET is underground? Could it also be built on the ground?
It's the Newtonian noise mitigation is the main drive. I said it as, going on the ground because we don't have space, but it is the Newtonian noise mitigation. That's actually the science drive.
I have a question for you. High power is always an interesting exercise. Do you know of any prototypes that are testing really high power that these future detectors are going to demand in suspended cavities?
There are some exercises in Australia. There is a prototype path towards generating high power in a suspended interferometer. However, at the moment, I think still the big machines are doing the brunt of that investigation, unfortunately.
There's one more. What is the influence of the laser wavelength that's used?
For using a different type of material test mass for silicon, you need to be transmissive of that material. So that will be 1 micron, won't be long enough. So hence you're going to the 1.5, 2 micron. At the same time, if you use longer wavelength, the scatter goes down by the 1 on lambda squared. So you have then the scatter in the interferometer will be less. So the idea there is, or is that the scatter, what we potentially now try to mitigate as much as possible in the interferometers, that with the longer wavelength, that will be less. So their performance will be better just based on that, assuming all the other challenges are overcome.
And like you said, you want to also use cryogenics for lower thermal noise at lower frequencies as well, and that also influences the laser wavelength you pick, right?
That is regarding then the silicon.
Yeah. Are there any more questions for Bram? Please feel free to raise your hands or post in the Q&A. I don't see any more questions for you, Bram. So thank you again for a lovely talk, and thank you to Edwige as well for kickstarting this session with some really lovely talks. And I think there's a short break before we jump to the contributed talks, and we will reconvene at 11 UTC, 11 European time, or 09 UTC. Was that right, Scott?
Yep, that's correct. Yeah, so we have basically 20 minutes from now. So yeah, we'll see people again in 20 minutes after the break. Thank you.
All right. Welcome back, everyone, to our contributed talks part of the session. These talks will be about 15 minutes long with 5 minutes per Q&A. And our first talk will be by Kirsty Gardner from the University of British Columbia on towards high throughput testing of low mechanical loss coating materials for gravitational wave detectors. So Kirsty, if you'd like to share your screen.
All right, looks good to everybody?
Yes, it does.
Okay, thank you very much then. Yep, my name is Kirsty. I'm a postdoctoral fellow at the Stuart Blossom Quantum Matter Institute at the University of British Columbia in Canada. And this talk is quiet coatings towards high throughput testing of low loss coatings using microresonators. So as we've heard, future generations of ground-based gravitational wave detectors will need new low noise coatings for the mirrors. We know from a bulk of research that if we're looking for a low noise material, we're looking for a material that has a low mechanical loss. So we can use mechanical resonators as test devices to measure thin film materials that are coated on top of them. And this is the standard way that these coatings have been tested, but they're tested typically using macroscopic devices. And as we know, the search for new materials is going to involve looking at a lot of different materials and a lot of different deposition parameters. So it would be really great if there was a high throughput testing method to increase the speed of the testing. So that's what we're working on at UBC. And instead of using macroscopic mechanical resonators, our approach is to shrink everything down to microscale mechanical resonators. And so with, say, 100 devices per chip, you can very easily imagine doing high throughput testing of these devices and therefore of the thin film coatings on top of them. If we have gradient coatings, then we can test many different film compositions on the same chip. And it's really easy during fabrication to change the geometry of these microresonators so that we can measure the loss of the materials at different frequencies, again, all on the same chip. And finally, it's really easy to integrate these samples into standard cryostat setups for low temperature testing, which is another advantage of this. So before I go on and talk about the work, I want to introduce you to the team who's doing this work and explain what their different contributions are. So on the theory and modeling side of things, we have Jörg Rottler and Stephen Blaber, who are doing atomistic simulations of materials to predict the mechanical loss. On the synthesis and growth side of things, we've got Ke Zhao and Fengmao Li, who do thin film growth of candidate materials by molecular beam epitaxy. On the characterization side of things, we've got Jeff Young, Matthew Mitchell, Henry Mullock, and me, and we measure the mechanical loss of the synthesized materials. And then Jess McIver, in addition to doing her own work, is our liaison with the broader gravitational wave community. And so our goal overall is to use the results of the characterization to feed back into the theory and modeling and the synthesis and growth to rapidly iterate and sort of enable this high throughput testing to find the best coating materials. So I'm going to start with a brief intro to the modeling of materials. This is work done by Jörg Rottler and former members of the group, Daniel Bruns and Daniel Wang. They're doing an atomistic exploration of two-level systems in amorphous silicon. Two-level systems are the things that are responsible for mechanical loss. And so what they're doing is molecular simulations of amorphous silicon using the Tursoff potential. And they're looking for which two-level systems contribute to mechanical loss and to predict the mechanical loss of a material, in this case, amorphous silicon. They've had some really nice results recently where they carried out these simulations at different search temperatures and found that no matter what the search temperature was, the data collapsed on a similar plateau, giving a mechanical loss of around 2 × 10⁻⁴. And the fact that no matter the search temperature, the results were pretty similar gives a lot of faith in the robustness of these models. And so what they're going to do next is to replace the Tursoff potential with an atomic cluster expansion formalism optimized with DFT data to further increase the accuracy of these models and get even better predictions of mechanical loss. Moving on briefly to the MBE system that we've got at UBC's Quantum Matter Institute. We're really lucky to have access to this system. It produces some very nice high quality thin films. And they have access to a large variety of materials. I'm not going to read them all out, but they're all on the slide. They can do amorphous growth of materials at low temperatures and crystal growth of materials at high temperatures. And so these are the folks that we give our samples to when we're ready to have the thin film coatings put on the samples. So now let's go back and have another look at these mechanical resonators that I mentioned before. When we're looking at new devices, the first thing to do is to run some simulations to see how these devices are going to behave. We use COMSOL, which is a finite element method software, to simulate the eigenmodes and the eigenfrequencies of the microdisks. So that's what shape do they oscillate with and what frequency do they oscillate at. And here I'm showing 5 mode shapes and eigenfrequencies of an 80 micron radius microdisk. And so these are our little mechanical resonators. Our lowest frequency mode oscillates at 65 kilohertz, and there are other mode shapes which oscillate at higher frequencies going from there. So I fabricate these in-house at the clean room at the Quantum Matter Institute. We start off with a standard silicon on insulator wafer, and we spin coat photoresist onto the top of that. And then we use optical lithography to pattern the photoresist. So we basically write into the photoresist and create the shape of the microdisc, the micro resonator that we want to produce. We then use reactive ion etching to transfer the pattern from the photoresist into the silicon layer. And at that point, the photoresist has done its job, so we can remove it. And then the next step is to create the pillar on which the microdisc sits. We do this using hydrofluoric acid, which selectively eats away at the silicon dioxide, but leaves the silicon untouched. And then we critical point dry the sample so that the discs don't collapse, but remain standing nice and free. And after this step, that's when we can do the thin film deposition and put the material on that we want to test. So here's an optical microscope image of some as fabricated microdiscs, just to show you what they look like. On the right-hand side, I've got a cross-sectional diagram of these discs with the different materials shown. We tend to put a coating on of thickness, maybe 10 to 25 nanometers, although we could go thicker just by extending the growth time. The silicon layer itself is 500 nanometers thick, and the silicon dioxide pedestal is 3.5 microns tall. And so the next step after fabrication is to deposit the thin film. So we deposited recently 25 nanometers of amorphous titanium dioxide at room temperature by MBE. And generally the way that the measurement for mechanical loss of the film is done is that you take 2 measurements. You measure a device when it's bare, uncoated, and then you do a second measurement when it's coated. And there's a formula that relates those 2 measurements. You measure the quality factor. And so there's a formula that relates the 2 quality factors so that you can extract the loss of the thin film material itself. And so what we wanted to do with this sample was to test whether it's possible to deposit the thin film on only half of the sample so that we could measure the bare disc quality factors and the coated disc quality factors at the same time, sort of put the chip in to be measured once and carry out those measurements in quick succession. So we covered the sample with aluminum foil to protect or to keep half of it covered while it was in the MBE. And you can see from the optical microscope image that that worked quite nicely. We have not quite half the sample, but half the sample is covered in titanium dioxide and half of it is left clean. Now, during the fabrication of these microdiscs, we made the choice to change the disc radius across the chip. So no 2 microdiscs are identical, which complicates a little bit the calculation of mechanical losses we'll see later, but otherwise this worked well. So here is our experimental setup. This is what we use to measure the quality, the mechanical quality factors of our microdiscs. So our chip containing the hundreds of devices is put into a vacuum chamber so that we can pump out the air and make sure that the pressure damping isn't limiting the measured quality factors. And our sample is mounted on a piezoelectric actuator, which itself is hooked up to a function generator. And so we can send a driving sine wave to the piezo actuator to start the discs oscillating, and then we can turn the signal off and measure how the amplitude of oscillation decays over time, which lets us extract the quality factor and then figure out the loss. We use a laser to do this measurement, so it's reflected off a mirror and then focused through a microscope objective lens onto a spot that we position on the rim of the microdisc, which I'm showing in the camera image in the middle of this slide. The laser is reflected off the microdisc and onto a quadrant photodiode, which is a position sensing photodiode. So as the disc vibrates, the reflected laser beam is also going to wobble. The quadrant photodiode lets us measure the position of that laser beam over time, which tells us what the displacement of the disk is doing over time. And so by measuring the laser position, we're measuring the disk position to measure its decay. And the output from the quadrant photodiode is hooked up to an oscilloscope, which is what we use for our data acquisition. On the right-hand side is just a photograph of a chip in our vacuum chamber, so you can see what it looks like. And for scale, you could hold that chip on the pad of your thumb or finger with a little bit of room to spare. So here is some example data. On the left-hand side, I'm showing how we call this a ring down. It's how the displacement of the disk changes over time. So you can see this decay over time. And you'll see in the time series data on the left that there's this interesting beat frequency. That's because the data that I'm showing here and the mode that we're measuring at the moment is this teeter-totter mode of the microdisk, which I've shown images of on the right-hand side. In a symmetric microdisk, there are two orthogonal modes that are degenerate. Because of the fabrication imperfections, a microdisk is very rarely perfectly symmetric, so that degeneracy is broken. And so instead of a single frequency, we see two very closely spaced frequencies. And so the graph on the right-hand side is the Fourier transform of the data on the left so that we can see what it looks like in frequency space. And you can see those two closely spaced frequencies, which is what leads to the beat frequency in the ring down on the left-hand side. So that at least helps us figure out how we fit our data. We need to use two decaying sinusoid terms, each with their own frequency, and we assume each one of them may have a different time constant and therefore a different quality factor. And so we fit our data with an equation of this form. And then typically what we do is take the average of the quality factors for those two modes to get a quality factor for the mode overall. So in the last few slides, I'll present some preliminary results from a couple of samples that we've made and measured recently. The first sample is the one that I showed earlier, where half of the sample was coated in titanium dioxide and half of it was left bare. As I mentioned, no two disks on this chip were identical, so the radii changed from 70 to 80 microns across the chip. And the frequencies of the disks changed from about 55 kilohertz to 60 kilohertz. There's a fair amount, so the Q factors are of order 2 times 10 to the 4 to 7 times 10 to the 4, so plenty large enough to measure the loss of titanium dioxide. But there's a fair amount of scatter in the quality factor data because of the change in radii across the chip. We have a second sample, which we made in a later fabrication run, and here we chose to fabricate the disks all with the same radii so that they would, in theory, all the disks would be identical, with the hope that this would reduce the scatter in the quality factor data. We also measured slightly high quality factors on this chip because we made some improvements to our vacuum chamber pressure, which is good. You can see there's still quite a bit of disk-to-disk variation in the quality factor because of fabrication imperfections. This isn't necessarily a problem. Going forward, now we know our disks are not going to be identical, and so we need to do measurements of a bare disk and then coat that disk and measure the same disk again. So we know what to do with this. Going back to sample 1, before we had figured this out, now I'm showing you, in addition to the quality factors of the bare disks, I've added on in blue the quality factors of the disks after we had put coatings on them. The quality factors of the bare disks are of order 10 to the 4, and the quality factors of the coated disks are of order 10 to the 3. We can plot instead the loss, which is just the inverse of the quality factor. That's useful because the formula which relates the loss that you measure of a bare disk and the loss that you measure of a coated disk to the loss that you want to extract of the coating itself uses the losses. And then it also needs the dilution factor, which is the ratio of energy in the film to the energy in the film plus the substrate, which you can calculate from COMSOL. And we get about 0.1 for this particular mode. And now for the final calculation, or estimate in this case, of coating loss, we have quality factors of one subset of uncoated disks and quality factors of a different subset of bare disks and a different subset of coated disks, which aren't identical, as I mentioned before. And so for this particular case, we're going to do a ballpark estimate of the titanium dioxide loss using the average losses of the bare disks and the coated disks. And if we do that, we get 2.3 times 10 to the minus 3 with an error of 0.7 times 10 to the minus 3, which comes from the standard deviation of the coated quality factors. So this estimate of the error here is sort of a large overestimate of the error that comes from doing this averaging and from the scatter in the data. Nevertheless, the value that we calculate is consistent with the literature values of 0.7 times 10 to the minus 3 to 6 times 10 to the minus 3. So that's great. This system is working as we would like it to, and it is capable of measuring the mechanical loss. For the next sample, sample 2, which we've just coated with 10 nanometers of titanium dioxide, we have measurements of the bare resonators, and we're going to measure those same resonators after they've been coated. So our error in calculation of the loss is going to be much less, which will be really nice. In terms of future work, where we're going with this long term, the next thing we're going to do is build a rigid optical enclosure to reduce vibrational noise. And this system will also include a scanning mirror so that we can work towards this high throughput part of this, so that we can automate these measurements. We're going to build a cryostat for cryogenic measurements of mechanical loss, because loss is not necessarily the same at cryogenic temperatures as it is at room temperature. And we're going to look at a method to measure the bulk and the shear loss independently, which will lead to a much more accurate prediction of coating thermal noise from loss measurements. So in summary, the atomistic modeling efforts converge on a prediction of loss angle. Our experimental setup for measuring microdisc quality factors and therefore the loss of thin films is operational. And our recent bring down measurements of coated and uncoated samples produce an estimate of titanium dioxide loss that's in agreement with literature values. So this all works. I'd like to acknowledge financial support from the NFRF, the Stuart Blossom Quantum Matter Institute, and CMC Microsystems. And I'd also like to acknowledge that this research was enabled in part by support provided by the CEDAR cluster through the Digital Research Alliance of Canada. And with that, I would like to thank you all for your time.
Well, thank you so much for that really lovely talk, Kirsty. Are there any questions for Kirsty? I don't see any hands up or questions on the chat. Oh, yeah, Edwige, would you like to ask your question?
Yes. Thank you, Kirsty. I had just a question on slide, I think it's slide 17, where you show the results, the measurement of the losses. Yeah, when you say it's consistent with literature values, I was wondering, the literature values, are they some values theoretically calculated, or is it some other measurements?
They were measurements.
Okay, thank you.
Yeah.
I don't see any questions, but I had a quick one, if you'll indulge me. How long does it take for you to go from fabrication to data taking? What's the time frame that we're talking about?
Yeah, good question. So once we've finished fabricating them, then they can go straight in the vacuum chamber for the measurements of the bare disk loss. With the current vacuum system, it takes maybe a day to pump down and stabilize it. That'll be improved once we've got a better vacuum system in the future, but currently it's a day, and then measurement of one device takes 1 to 2 seconds, and then 30 seconds to a minute to move to the next device.
Yeah, thank you. I don't see any more questions, so I'd like to thank you again for the really lovely talk, and welcome our next speaker. Our next speaker is Steve Penn, and he'll be talking on improved sensitivity in next generation ground-based gravitational wave detectors using substrate transferred AlGaAs coatings. So the floor is all yours, Steve.
Well, if you've been following your schedule, you probably noticed that I'm not Greg Harry. Greg had a family medical issue, so I subbed in at the last minute to give this talk. Okay, we're going to talk about AlGaAs mirror coatings for improving sensitivity in gravitational wave detectors. And I'm going to pick up a little bit on some cues that Bram talked about in his slides when he was talking about A#. So first, this is a mixed community of people that are involved in detector science and astrophysics. For the astrophysics people, they might not be very familiar with AlGaAs. So why should astrophysicists care about AlGaAs? And let me say, when I say the word AlGaAs, what I mean is that's short for substrate transferred crystalline gallium arsenide, aluminum gallium arsenide mirror coatings, but we just call it AlGaAs. And the reason they should care is that the sensitivity of LIGO sees a significant improvement if we switch from amorphous coatings to AlGaAs crystalline coatings. AlGaAs thermal noise, coating thermal noise, is several times lower than the current coatings. And in fact, when we see these published noise curves, they only list the upper limit of what we think the coating thermal noise is. We're trying to complete measurements this summer, as I'll refer to later, that are going to measure it directly. But right now, our coating thermal noise apparatus is not sensitive enough to measure the actual coating thermal noise of the AlGaAs coatings because it's so low. And what this gives us astrophysically is higher event rates, better signal to noise ratios, and sensitivities for room temperature detectors that will compare with the designs for cryogenic upgrades. And the huge benefit there is that the room temperature detectors are less costly, there is less downtime, and there's less complications from going to a cryogenic system. It's basically known technologies that we can use by increasing the laser power, increasing squeezing, increasing the test mass size, and switching to crystalline coatings. That also means that that translates into more astrophysical detections per year. So if you're looking at the noise curve that's plotted there, if we hopefully get to the A+ design, it should have this sensitivity shown in this reddish brown color. As you switch to A#, in the post-05 committee report, they investigate A# and they choose to still use the A+ coatings. And if you do that, you do get an improvement mostly from larger test masses and the increased laser power and increased squeezing. But if you add on to that now a switch to AlGaAs coatings, you double that detection rate. It's sort of average doubling over the 3 different sources just by switching to AlGaAs coatings. And this, I'll point out, is still using the upper limit. These detection rates are probably much better. That also gives us signal to noise ratio improvements. So if we were looking at, for example, 150914, if we had AlGaAs coatings in the A# detector, we would have a signal to noise ratio of over 200. And now we can start to investigate things like alternative theories of gravity, etc. Similarly, if we were looking at 170917, excuse me, that should be 170817, the signal to noise ratio goes up now to over 300, and we can start to investigate the properties of the neutron star, the equation of state, better comparisons of the speed of gravity versus light, etc. And as Bram also mentioned, the 2 big improvements that are happening in the central noise bucket for LIGO are reducing the coating thermal noise and increasing the squeezing. Now, it's, squeezing is a great technology, but if you don't pair that with an increase in the coating thermal noise, then a lot of the benefit from the squeezing is lost. As you can see here, if you cannot lower the coating thermal noise, then you can't bring down the sensitivity even in areas where the squeezing curve is low. So in order to take full advantage of squeezing, we need the lower coating thermal noise. And the only coating that can provide that thus far is AlGaAs crystalline coatings. So what is AlGaAs? It's different than the coating technologies that we've used thus far in all gravitational wave detectors. It's a crystal. It's grown via molecular beam epitaxy on a single gas wafer. It's a multi-layer, single crystal, but a multi-layer where you change the doping level of aluminum, replacing the gallium in order to change the index. The specific AlGaAs layer has a lower index, and the gas layer has a higher index, and you pair those together to make a Bragg reflector. Then the wafer is etched away and the coating is transferred over to the substrate. This was a difficult technology that took us a lot of years to work out the kinks and lowering the noise that was involved in that transfer and bonding process. But now that is done, we're getting very good results overall. And this allows this coating to be used on a wide variety of substrates and anything that is above the band gap up to about 4.5 microns. Now, of course, coatings have to have good mechanical properties and good optical properties, but AlGaAs has excellent optical properties as well as excellent mechanical properties. So you can see that you get very low scatter, very low absorption, good uniformity, high laser damage threshold, and excellent finesse for these coatings. Now, most of the high precision timing and frequency community uses AlGaAs coatings in their fixed cavities because that's what gives them the lowest noise. But those cavities and a lot of the coatings that we've tested thus far are all use rather small coatings, small diameter coatings. And the challenge for us going forward is making larger diameter coatings. So we are now investigating 10 centimeter coatings, and we've recently gotten funded to test 20 centimeter coatings. And then to actually implement these in A#, we will need to expand yet again and go up to 30 centimeter coatings. So this is an example of a 10 centimeter coating that we've recently measured at Caltech. Now, how do we scale these? There is a large technical paper that we've written that goes through this in detail, but essentially we are working with 3 industry partners in order to do this. Freiberger Technologies grows the original gas wafers that are then grown in a very large boule that takes a few years, cut, polished, waferized, and then they are passed on to EVG, which is the MBE facility, the molecular beam epitaxy facility, where we will actually grow the coatings. And this is all administered by Thorlab Crystalline Systems, which is led by Garrett Cole, who originally developed these coatings. And that process from the original boule growth through to the development of the coatings will take about 3 years. So when we're thinking about A#, we have to actually begin this process relatively soon if we want to have good results in time for that upgrade. So maybe people in the instrument science community have heard of AlGaAs, but maybe other people that are attending the conference haven't. So I just want to give you a flavor of the sort of support and discussion of AlGaAs coatings from 2 independent groups. One is the LIGO Post-05 committee. And as you can see here, what they're recommending for A# is the crystalline coatings because they provide the best option for significantly reducing the Brownian thermal noise. And in fact, there is no amorphous coating that comes even close to the low thermal noise that's provided by crystalline coatings. And then while I don't have a direct quote from it, LIGO really recently underwent a review by the NSF, and they specifically called out that we need a great deal of improvement in coating thermal noise, that the situation is becoming urgent, and they advised us to continue the development of AlGaAs as the best candidate to solve that problem. Now, I've mentioned a couple of times about AlGaAs's direct measurements of coating thermal noise. These are conducted at MIT. There was an experiment that was developed and is run by Matt Evans, Slava Gras, and Nick Demos. And using a thermo-optically optimized AlGaAs coating, they made the measurement that is shown here. Hopefully you can see my cursor moving around, where they made an estimate over a wide range of what the coating thermal noise probably was. And the reason that it's just an estimate is because the noise was dominated by the apparatus itself. Specifically for this folded cavity, you have what are the input and output coupling mirrors, and they have an amorphous coating, and the coating thermal noise in these coatings were actually the dominant source of noise. So in order to try and actually make a direct measurement of the coating thermal noise, we had to investigate getting new coupler mirrors, which we've now done. We got AlGaAs coupler mirrors. These were very challenging to make, and because of their unique nature, quite expensive actually. So these just arrived earlier in the summer, and they're about 1/2 inch in diameter, 5 centimeter radius of curvature, and about $20,000 each. But we're hoping that by the end of the summer, we can have a direct measurement so we actually know how low we can drive the noise level with AlGaAs coatings. Now, to model the loss, there's 2 projects underway. Andre Grederson from Embry-Riddle and Simon Tate from Glasgow have been working together on a room temperature mechanical loss model. And thus far, it's in good agreement with the current existing room temperature measurements on AlGaAs. That paper is under preparation and hopefully release in the next few months. And in addition, there were recent cryogenic Q measurements made by Nick Didio and collaborators at Syracuse. And I'm currently working on modeling the thermoelastic loss so that we can properly extract the mechanical loss from those measurements. And that paper is also under preparation. Now, one thing that's different in AlGaAs versus amorphous coatings is that it's birefringent. And so there's an investigations on both small and large optics. The small one's already underway. Andre and Ellie Grederson from Embry-Riddle have been conducting measurements on small optics where they raster over the surface. What's shown here is a picture of comparing amorphous coating, so this is a tantalus silica coating, as was used in initial LIGO, and an AlGaAs coating, and you can then see the increased birefringence. So this is a relatively recent measurement, but their plan is to move to larger diameters and get more detailed scans as they develop the experiment. And a proposal was put in by me and Stefan Ballmer at Syracuse and Andre Grederson to study the birefringence on larger optics. So this will fund the development and study of 20 centimeter AlGaAs optics and have the capability for measuring the birefringence and mapping the birefringence up to and including the test masses for both A sharp and even could be extended for use for the test masses for Cosmic Explorer. This proposal has now been recommended for funding. In addition, there's an experiment that's occurring at Syracuse that's being led by Satoshi Tanioka about developing a arm-length stabilization system. Because of the band gap in AlGaAs, we can't use the green laser light to stabilize the arm cavities. So instead of using a frequency doubling, we're using a wavelength doubling technique. So locking a 2128 laser to the main 1064 laser and using dichroic coating so that we have a low finesse 2 micron and high finesse 1 micron cavity. And then basically the same system that is currently used to lock the arms in LIGO will be used. You're just using twice the wavelength instead of half. But the same locking procedure occurs. Okay, looks like my time is up. So in summary, let me just say, AlGaAs is really a game changer. I know it's different technology than we've used in our other mirror coatings, but it presents to us an immense opportunity to take what has been a 20-year-long campaign to solve the coating thermal noise problem and basically eliminates it. The coating thermal noise is so low. But it takes a significant investment of both money and resources in order to grow these coatings to the appropriate size. But that's an engineering challenge. So we have coatings that fulfill the optical and mechanical specs. We just now need to put the money in order to grow them to the sizes that we need. So we need 30 centimeter coatings, and that is expensive. We estimate about 22 million and 3 to 5 years. Right now is a time for us to get started by giving a few million to start the crystal growth process. That's really the long time requirement here. Start that now, and so that we can have these coatings ready in time for A sharp. With that, I thank you and open the floor for questions.
Yeah, thank you so much for that lovely talk, Steve. Are there any questions for Steve? I don't see any hands up, but I had a quick question, if you'll indulge me. So do you know off the top of your head what the surface figures look like for a mirror with AlGaAs coatings and a mirror with the current LIGO mirrors?
What looks like?
The surface figures. So what's the best we can do in terms of surface roughness when you have the AlGaAs coatings on silicon mirrors, for example?
Yeah, so there is here. Well, maybe it was in the previous slide deck. So the one benefit that you have right now is that when you produce the AlGaAs coating, you're etching away and you have this etch layer. And so once you produce that, you can then go back through and ion polish. So if you just do that rough etch, then you have a sort of few nanometer variation. And now you can go back through and do an ion polish just like you do on the mirrors and get that down to the, nanometer or sub-nanometer.
Thank you.
Edwige has a question.
Please go ahead.
Yes, thank you. Hi, Steve. I had a question about the birefringence issue.
Yes.
You talked about several 1 or 2 experiments aiming at measuring this birefringence. Do you feel this is a big threat to this technology? Do you have already some information how it can limit the performances of this the AlGaAs coating?
Well, right now, for the fixed cavities, they also have birefringence in them, and they just use one of the polarizations. We need to, one of the things that's on our list to investigate is using a suspended cavity with larger mirrors to see if motion coupling, for example, from the beam splitter might create some mixing in the polarizations. So this is an active area of investigation. But our thought is that probably this will lead to a small amount of loss, but not enough at this point to concern us. But we still need to investigate this. So for example, looking at thermally induced birefringence. So if you have thermal gradients, that can cause stresses. And so we have to look at the level of thermally and stress induced birefringence and see if that is going to present a noise level that we need to concern ourselves with. So it's one reason why we're doing these investigations. But right now we don't have any red flags to indicate that it's going to be a problem.
Thank you.
Great. Thank you so much again, Steve, for a really lovely talk. And the last speaker for our session today would be Andre Lode on dual balanced readout for scattered light noise suppression in interferometric detectors. Andre, would you go ahead and share your screen, please?
So, okay. Good morning from Hamburg. Thank you, Vaishali, for welcoming me. I'm going to talk about a bit of a niche subject, namely scattered light noise suppression. And I hope at the end of the talk, I'm going to be able to convince you that it's a relevant and growing problem, actually, and that we may have found part of a solution, which we call dual balanced readout. And I'm going to dive into the details soon. But first, let's start with a short introduction on why scattered light is a big problem. So here to the left, you see a bit of old noise budget. We've seen newer ones today, but I hope it doesn't matter. And in purple, you see the scattered light curve, the known scattered light noise contribution that we have in O3. And it's estimated that there are more scattered light noise contributions, especially in times of higher seismic noise. And we know that it's going to be a major limitation, especially also for future detectors, with scattered light noise limiting the detection with just a few or even single photons that are scattered in the wrong way per second. So just to give you another idea, what does this look like? Typically, we can see in these spectrograms that the scattered light noise event, which you see on the right, looks a bit different than the typical gravitational wave transient that we expect. As in here, it shows multiple arches, and usually we are able to distinguish these glitches, but it's still able, I mean, scattered light noise is still able to hide gravitational wave transients, and it's definitely reducing the significance of strain data if there's a gravitational wave transient present. So it's definitely a problem. And now we're going to have a bit of a look into the general mechanism behind scattered light. So you see here a rough scheme which shows that some light may scatter off of a test mass. So in this case, you see a Michelson interferometer, you see some light scattering off from the east test mass, scattering away to, let's say, tunnel walls or whatever, and then scattering back into the interferometer. And the scattered light always becomes a problem then when both the backscattering surface is moving and when the photons are really hitting the photodiode. So they are coupling back into the interferometer mode or into cavity modes in case of cavities. And scattering can occur due to any reason. So we all know that optics can't be absolutely perfect, so there will always be some scattering occurring. And if we're not able to mitigate the recoupling into the interferometer, then it's just annoying. And to give you an idea of what kind of vibrations we're talking about, there's, for instance, the story of ravens pecking on the ice. So at LIGO, there used to be ice building up at one of the end stations due to at an AC unit, and since there were ravens who were really thirsty, came to the ice to peck at it, these vibrations coupled into the interferometer onto the vacuum pipes, and they led to the pipes vibrating and scattered light being modulated. And so you can see that there are a lot of types of vibrations that could potentially make scattered light noise couple into the interferometer. So we're working on ways to mitigate scattered light, but what is currently being done is typically the use of baffles. So you can imagine around the vacuum pipes in LIGO and other detectors, there are a lot of these baffles, basically leading to apertures that limit that avoid the test mass seeing the tunnel walls, so to say, such that there's no way that light scattering from the test mass away onto a tunnel wall can directly go back into the cavity mode. However, these baffles also produce some scattering, and due to their limiting aperture, and we haven't found an ideal solution yet. Another way is to tediously identify all types of scattering sources, but this also doesn't lead to a full mitigation of scattered light noise. So here in Hamburg, we're working on different techniques, and these exploit differences between gravitational wave signals and scattered light signals. So in the case of the dual balanced readout scheme that I'm talking about, we can see that if we have a look at the electric field in a quadrature picture, then we can observe that at the antisymmetric port, so in the south of the scheme that you see here, a gravitational wave signal leads to an amplitude modulation of the light. So we observe it in what we call the amplitude quadrature, and a scattering event can lead to both a phase modulation and an amplitude modulation. So we observe it in amplitude and phase quadrature. So just to say that here, there's a clear difference between gravitational waves and scattered light noise, and we're exploiting this difference. And how we're doing this is by implementing an additional readout of the interferometer. So this is something new, brand new, basically. We are also reading out the light back reflected. So typically in your microscope interferometer or an enhanced interferometer, you would read out only antisymmetric port, given that it's operated at dark fringe. But we implement an additional readout. Here it's a balanced homodyne readout for both of the ports to exploit that additional information that we have about scattered light. So then, in addition to reading out at different ports, we also read out at different quadratures. So we're interested in reading out, for instance, the phase quadrature at the west port, so the light back reflected, and the amplitude quadrature in the south, so the typical port that you read out. But it doesn't have to be like that. It's just necessary to be orthogonal quadratures. And as it turns out, if we combine these signals that we use, so here with PW, I denote the phase quadrature at the west port, and with XS, I denote the amplitude quadrature at the south port. If we combine these signals in a linear combination, so from the difference or the sum, we can read out both interferometer arms separately. And also remove the scattered light noise from each other arm. So assuming we have, for instance, scattered light only in the, let's say in the west arm, in the east arm, I'm sorry, then we can read out the north arm, phase variations of the north arm, and we will not see the scattering from the east arm. So that's the idea. And it shows that, at least in simulations for now, we've been able to show this. So if we have a look at these signals, and in comparison, I also brought a DC readout here in the right plot, then we can see that assuming I inject a phase change in both arms, so gravitational wave changing both interferometer arms, and scattered light only in one of the arms, we can fully remove the scattered light noise from in one of the signals, and in the other one, so in the red one here S1, and in the other one, which is the black one, we see that there's the scattered light noise is enhanced. So we're able to partially subtract scattered light noise, and there's actually no limit except shot noise limitation. So just to keep that in mind, by reading out these quadratures, theoretically there shouldn't be a limit basically on the scattered light noise mitigation. Now, we've been able to show this in the lab, and here is a setup for you to have an idea of what exactly we've been doing in our lab. And that is, we set up a Michelson interferometer with a scattered light noise source in one of the arms. So here in the east arm, we have a partially reflecting window. We have a scattering that we can modulate the scattering arm. And we also modulate in the north interferometer arm to get a artificial signal. So to inject a gravitational wave basically into our interferometer. Then we used a homodyne detector, which just subtracts basically the powers from both arms to be able to lock the interferometer at mid-fringe in this case, but the whole subtraction scheme doesn't rely on the operating point of the interferometer. And in addition, we set up two balanced homodyne detectors. So again, homodyne diodes, they are subtracting the powers from each diode. And we tuned these balanced homodyne detectors to orthogonal quadratures. And now we've been able to show that actually we're able to remove some of the scattered light noise. So in our very rudimentary experiment here, this is actually the first measurement that really worked out from last week. We are able to show that using the scheme, we can reduce the scattered light noise by about 8.3 decibel. So we have a better signal to noise ratio if we just compare the amplitude spectral density of a signal, which we have on the left here, to a scattered light noise peak, which we see on the right. So the blue line depicts here the signal that we observe on the homodyne detector, the HD, which we also use for locking. And S1 is the linear combination of our balanced homodyne detector signals. So 8.3 decibels, I think for the first measurement, that's quite okay. So yeah, as you've seen, that was only a Michelson interferometer. And that's actually one of the biggest challenges that we're facing here in the dual balanced readout scheme. Of course, LIGO and Virgo Kagra, they don't consist of a simple Michelson interferometer. They are more complex than that. So a lot of time will go into investigating how to apply the scheme to an enhanced Michelson interferometer with all the cavities and squeezed vacuum and so on. And a bit more work will also go into improving our preliminary results by achieving shot noise limitation and just improving the technical problems that our experiment is still facing. And of course, one thing you might stumble across already, they want to read out the bright light coming back from the interferometer. That's also something that we need to work on for a bright readout. it might be necessary to implement something like optical AC coupling. So that's definitely something that we have in mind, but there's also some more work to be done. So to summarize, I hope I've been able to convince you that scattered light noise is a problem, and that it is going to be more important as we go to more sensitivities, to better sensitivities, and that with the scheme that I just briefly introduced, we are able to get ahead of the problem a little bit. We've achieved a proof of concept of reducing scattered light noise, at least partially, and it seems like we can progress a bit further with that even. So with that, I would like to thank you, and if you have any questions, feel free to ask them now.
Thank you for that really lovely talk, Andre. Are there any questions? I don't see any hands up. I see one from Benno. Have you analyzed the effect of technical laser noise at the bright port readout, which might be orders of magnitude above short noise?
A technical laser noise like frequency noise, amplitude noise. For the experiment yet, no, we don't have an amplitude stabilization, but we're planning on doing that. And frequency noise is also definitely a problem, since the interferometer arms have a different way than just the local oscillator of the balanced two-mode detector. So we are aware of these problems, but experimentally we're not there yet.
Are there any more questions? I have one, if that's okay.
Sure.
Do you care about the relative phase of the two local oscillators that you have at the two readouts? Or do you need to care?
Yeah, so for the local oscillator phases, I said usually what we want to achieve is we read out the amplitude quadrature in one port and the phase quadrature in the other port. So that's 90 degrees of phase difference between the local oscillators. And as far as I'm concerned, I believe that it doesn't matter exactly which quadratures you read out, as long as these are orthogonal quadratures. So there's a 90-degree offset of the phase of the local oscillator.
Sorry, and just you're looking at mid-fringe because that gives you the highest signal to noise ratio, and that's a great point to start your experiment, I guess. Okay.
Yeah.
Are there any more questions? I don't see any in the chat either. So thank you again for the lovely talk.
Thank you.
And I'd like to thank all the speakers today, especially those for whom it was in a really awful time zone. It was a privilege to listen to all these wonderful talks. And if there are no more announcements or anything to be made, I'll see you all in the other sessions then.
Yeah, great. And thank you very much, Vishali. The next session will start in about 4 hours. Hope to see many of you there. Take care, everyone. Bye.
See you.